Okay, as we saw in the last clip, as omega 1 approaches omega naught, the system that we've been talking about will approach resonance. In this clip, we're going to look at the differential equation for the case where the driving frequency is equal to the resonant frequency of the oscillator itself. So you can imagine exerting a sinusoidal force function that matches the frequency, natural frequency of a swing. So this is the equation for an oscillatory system in which the driving force is at the same frequency as the natural oscillation. Now the solution to this equation is pretty straightforward if you understand the material that preceded these applications, the material on finding solutions to non-homogeneous equations. If you remember, then we can use the method of undetermined coefficients. We know that we want to try particular solution form that's a combination of sines and cosines of omega naught t, but we know that we can't do that because sines and cosines of omega naught t match the solutions to our original homogeneous equation, our characteristic solutions, our fundamental set. So as we've done, and without going through the theoretical reasons why we would, you recall that we put a t in front of each of these functions so that our particular solution has the form at cosine omega naught t plus bt sine of omega naught t, and then we simply run through the usual steps. And I'm not going to run through those steps now. We've run through them a number of times. But we simply evaluate the constants A and B. We plug this solution back in here and find out what the constants A and B have to be equal to, and it turns out that A is going to have to be 0, and B is going to be just F over M divided by 2 omega naught times T sine of omega naught T. Now I'm going to stop for a second and correct a little blemish right here. Okay, that wasn't actually a blemish, that was a 0 I wrote here. Once I got to writing zeros on my omega naughts, apparently I just got in the habit and put one up here where it would have been in an exponent, so it's just a kind of a typo, except I wasn't typing. Now, this particular solution leads us to the general solution where, as we know for this function, and as we should be very much accustomed, particular solution, the characteristic solution is just C1 cosine omega naught t plus C2 sine omega naught t. And then we have the particular part of the solution, and this kind of got bunched up over here, but that's just the same as what I wrote here. Now we can observe that for small values of t, since this solution has the factor t, if t is small enough, then this particular solution is not going to amount to a hill of beans. But as t gets large, this particular solution, the coefficient of our sine of omega naught t is going to become increasingly large, so that this particular solution is going to represent an oscillation with angular frequency omega naught, with an oscillation equal to that of the natural frequency of the system and of unlimited increasing magnitude. And once t gets big enough, whatever the coefficients C1 and C2 are, they are constant, so that the amplitude of these oscillations has to be limited. This is not limited, so that in the long run the behavior of the particular solution is what dominates the behavior of the solution to the equation. So that whatever happens here in the early going, which might be just about anything, we could have something that does this. Okay, I'm not drawing that very well, but eventually those oscillations are going to become insignificant, and we're going to settle down into the oscillation governed by the particular solution. And those oscillations are going to get wilder and wilder. And that's very similar to what we saw with the solution, or with the well, in the last clip, the whole phenomenon of resonance. And I'll mention here that the slopes of this linear tangent line envelope are plus or minus f over m divided by 2 omega naught. And those slopes are pretty much the same no matter what the value of omega 1, as long as it's very close to that of omega naught. So we can put a very clear meaning on the solution of this differential equation. Now, as I've mentioned, no system really continues to increase its amplitude forever. That would take eventually use up all the energy in the universe. There's got to be something that limits this kind of resonance, and that's going to be some kind of a drag. And we can understand that in terms of the drag on a pendulum or a swing. If we continue exerting a force at the natural frequency of the swing, the oscillations of the swing are going to get bigger and bigger, and maybe more or less in a linear fashion. There are energy considerations that kind of make it actually difficult to do that in practice, but theoretically that could happen. But in the case of a swing, there's always some kind of drag. In the rope, there's air resistance. There are factors that make it impossible to continue this approach to the ideal resonance. And what's going to actually happen is these straight lines will, in practice, start to curve inward, and there will be some kind of a limit on this envelope and some kind of a limit on the oscillations that can occur. Some kind of limit on the amplitude of the oscillations. And that's going to be limited ultimately by the energy that's available to drive the system. So in the next clip, we're going to look at what happens with a simple rule for drag on the system.